Welcome to Miss Math Presents Genius Geometry, G10 Polygons. The first thing about polygons is we have to know the names. 3 sides is a triangle. 4 sides, a quadrilateral. 5 sides, pentagon. 6 sides, hexagon. 7 sides, heptagon. 8 sides, octagon. 9 sides, nonagon. 10 sides, decagon. 12 sides, dodecagon. We don't have names for every single possible combination of sides for polygons. So, at some point after n sides, we start calling them n-gons. For example, a 28-sided shape would be called a 28-gon. For the formulas that we have for our polygons, before you know which formula to use, you have to ask a couple of questions. First, is it an interior angle? Or is it an exterior angle? Are we looking for the sum of the angles? Or are we looking for one angle? If it is one angle, is it regular? The interior angles add up to n minus 2 in parentheses times 180, with n being the number of sides. Exterior angles, the sum of the exterior angles of a polygon is 360, no matter how many sides we have. Now for one angle, the polygon does have to be regular, meaning all the angles are the same. They're all congruent. And all the sides are congruent. So one interior angle is n minus 2 in parentheses times 180 over n. And what you'll notice is this is the same as the sum on the top divided by the number of sides. For one regular exterior angle, it's 360 divided by n, or the sum over the number of sides. So you notice for one, we take our formula for the sum and divide it by n, both for interior and exterior angles. I would strongly recommend write your formulas down. We do remember things a lot better after we've written them down. So that is definitely a trick you can use to help to remember them by. So let's try some. What is the sum of the interior angles of a 30-gon? So I'm going to take my formula that I wrote down. The sum of the interior angles is n minus 2 times 180. And I know that n is 30. So I'm going to replace n with 30 and plug that into my calculator. And I get back 5,040. What is the measure of an exterior angle and a regular 20-gon? Well, this does say an exterior angle, so I'm going to look at my formulas that I wrote down, and one exterior angle in a regular polygon is 360 over the number of sides. So I know that n is 20, so I'm going to replace n with 20, and we get 18. What is the sum of the measures of the exterior angles of a decagon? So we're looking at sum, we're looking at exterior. Well, that's always 360 according to our formulas. And the number of sides doesn't matter, so it's 360 degrees. What about solving for x? In Polygon Senior, angle E is congruent to angle O. What is the value of x? If I look here, I have a 6-sided polygon, or hexagon, and in 5 of those, I have terms of x written as our angle measurement. So even though x is in each individual angle, it's not a regular polygon. So when I'm looking at my formulas, I have to use the sum of interior angles. I can't use one because it's not regular. So the first thing I'm going to do is, I see here that E and O are the same. I do want to make sure I have something for every angle. So since O is blank, I'm going to copy what I see at E, x plus 100 degrees, and I'm going to add that right here for angle O. Now, if I'm going to have the sum of these, I have to know what they're going to add up to. So I'm going to take my formula for the sum of the interior angles, and it's a hexagon. I can count 6 sides. So I can replace n with 6, and I get that these angles should all add up to 720. So I'm going to type them all out in my calculator or in Desmos, and then I'm going to set it equal to 720. So when I finish typing it out, it's going to look something like this. You do want to make sure you have every angle here. I have a hexagon, so I should have 1, 2, 3, 4, 5, 6 angle measures that I'm adding up, and it equals 720, which is what I found for my sum of interior angles. Once I solve this, I'll find that x equals 30. Sometimes we have to use our formula to work backwards to figure out how many sides there are. It's not that much different from what we've been doing. We're going to plug in x for what we don't know, and we're going to fill in what we do know. So here, we have a rectangle that's covering part of a regular polygon. How many sides does the regular polygon have? So I can look here and see that I have one angle. It does tell me it's a regular polygon, and I do see its interior it's inside the polygon. So I'm going to use the formula for one regular interior angle, and that's n minus 2 in parentheses times 180 over n. Now, I do see that one interior angle is 108 degrees, so I'm going to replace that part of my equation with 108. I always use x for what I don't know, so if I don't know the sides, that's where x is going to go. So this is the equation that I would solve, and I find that x is 5. Bonus question, what is the name of this polygon? You guessed it, it's a pentagon. Let's look at composite figures. What composite figures are figures that are pasted together or put together. The figure shown is composed of a square and a regular hexagon. What is the measure of angle A? I call this a pizza problem because what I do is I draw a circle around where that angle is I need to find, and I kind of think about this like a piece, like a big pizza. A circle, or pizza, is 360 degrees. So if I treat the different portions of the polygons as slices, I can find each slice to see what's going to be left over. So first, let's look at our square. Our square has corners that are 90 degrees, so this slice that I'm taking out of my pizza is 90 degrees. Next, I need to figure out what this slice is for the hexagon. So, one regular interior angle equals n minus 2 in parentheses times 180 over n. It's a hexagon, so I'm going to plug in 6 for n. And that tells me that that slice is going to be 120 degrees. Now that I have those slices, I can take the whole thing, 360, subtract the 2 that I got, 120, and 90, so I'm taking away those 2 slices. And what I'm left with is 150. So the measure of angle A is 150 degrees. Let's look at tessellations. In a tessellation, you take a polygon, and then you can repeat it and it can keep on going forever without any gaps or overlaps. A regular polygon can be tessellated if its interior angle is a factor of 360. So let's take a look at how we would figure this out. One interior angle of a regular polygon is n minus 2 in parentheses times 180 over n. So let's try this with the triangle first. We know a triangle has 3 sides, so 3 minus 2 in parentheses times 180 over 3, and that equals 60. So next, I need to figure out if 360 is a factor of, if 60 is a factor of 360. So I can take 360, divide by 60, and I want to get a whole number if that's a factor. So 360 divided by 60 gives me 6, which means that, yes, a triangle can tessellate. Let's look at a square. Same thing, one interior angle, I'm going to plug in 4 for n. 4 minus 2 in parentheses times 180 over 4, I get 90. 360 divided by 90 gives me 4. So that is a whole number. 90 is a factor of 360. So yes, it can make a tessellation. Let's look at a hexagon. 6 minus 2 in parentheses times 180 over 6 gives me 120. 360 divided by 120 is 3. So yes, it can make a tessellation. What about a decagon? A decagon has 10 sides, so we're plugging in 10 for n. 10 minus 2 in parentheses times 180 over 10 is 144. 360 divided by 144 is 2.5. Not a whole number. 144 is not a factor. So no, it cannot make a tessellation. Fun fact, the only regular polygons that can be tessellated are triangles, squares, and hexagons. Thanks for joining me for today's edition of Ms. Math Presents Genius Geometry. See you next time.